Hi everyone, this is ME475 Final Project Bike Frame Analysis by Jason Kim and Vince Rende. The objective of this project is to analyze a given bike frame under certain load scenarios considering weight, stiffness, strength, buckling, fatigue, and dynamic behavior. Analyzing this bike frame is going to be done using beam elements, detailed models of critical joints, and the results must be validated.
Here are the material properties for steel tubing used as a reference frame. Here are the material properties for aluminum using the alternate design. And here are the cross-section dimensions for both the steel and the aluminum, and we have the diameters for both the outer and the inner. The weight of the reference frame steel came out to be roughly 7 pounds, and for aluminum, it came out to be roughly 5 pounds, which is about 25% decrease. Load scenarios considered was frontal impact, front tire over a bump, and rear tire over a bump. Conditions for the frontal impact applied is 2 Gs in the Z direction at 0.4. And here are the stress distribution for the frontal impact for the steel property. Here are the stress distribution for aluminum frame, which has lower extreme compared to the steel frame. These stresses contribute to the deformation for both frames shown below. Conditions for the road bump at the front tire includes a positive force applied in the Y and the Z direction at 0.4. Here is the combined stress distribution for the steel frame, and we can see here is the maximum stress occurs at the back of the bike, whereas the minimum occurs at the front. Here is the combined stress distribution for the aluminum frame, and like the last load, it has lower extremes compared to the steel frame. Here is the total deformation for both frames, and again, the aluminum has a higher deformation. Conditions for the road bump in the rear tire includes a positive force being applied in the Y and the Z direction at 0.1. When examining the combined stress distribution for the steel frame, the minimum and maximum occurs at the same place. As seen here, the behavior is the same for the aluminum frame, except that the extreme is lower compared to the steel frame. When comparing the deformation between the two frames, it is shown again that the aluminum has a higher deformation than the steel.
Along with the structural analysis, there was also a modal analysis done on this frame with the rear axle fixed. As you can see here, for both steel and aluminum, the first mode resulted in relatively low frequencies. A road bump at the rear tire had a higher impact than at the front tire, so a harmonic analysis was done with this load scenario, shown here with the highest amplitude at a relatively low frequency. This harmonic analysis was also done on the aluminum frame with, again, the highest amplitude at a low frequency. The frontal impact load scenario had the most impact on stress concentration and deformation, so a buckling analysis was done for this, with the load multipliers of 3.8 and 2.7 for steel and aluminum respectively. Due to such high stress concentrations, the shell analysis was also done with this frontal impact load scenario at the joint seen on the right here. The total deformation and equivalent stress distributions for the steel shell analysis can be seen here. Similarly, these results can be seen for the aluminum shell analysis for the alternative design here. When analyzing these solutions, it makes sense that although the aluminum frame has the lightest weight, it could be considered a useful design for this collapsible frame. Also, the frontal impact at 2 Gs appeared to have, again, the most catastrophic reaction, so it was used for the shell analysis because it had the most critical joints. Modal frequencies and harmonic frequencies had low values because the frame is not necessarily designed to handle these harmonic loads. And finally, the buckling analysis had low load multipliers because bikes are not necessarily designed to handle such harsh loads.